Okay, here we are back for the last section of content for the Queen Step test, instrumented case study. In the last video, we saw the breakdown of the biomechanics. We quickly had taken a look at the force plate data that allowed us to confirm step timing, step rate, and these peak landing forces and these propulsive forces. So those are things that are generally classified as biomechanics data. It informs the physics. Those are kinetic data here. Down in this, we can see this is the low back Z axis is the vertical position. So the participants started with their lower back marker was pretty much exactly 1 meter off the ground. And as they went up onto the step, they traveled about 0.3 meters. So we can see the kinematics here. What you'll notice on the left, we've got a whole list of blue. These are markers, the 3D coordinates of all of these lit up markers on the skeleton. They've been tracked through the software, and then we've calculated several angles, and we'll talk through that. So this is going to be the kinematics, these kinetics, forces, and kinematics descriptions of movement will combine. And again, those are traditionally the biomechanics lens products. But what we're going to talk about in this context is how we can use these data to inform our understanding of the motor control, the movement strategies that are being deployed by this participant as she executes the 3 minutes of vertical stepping. So we started off with the Queen Step test as it's prescribed. Then we've added the metabolic cart. Then we've added the biomechanics lens with the mechanical efficiency calculation. Here, we're going to land on something that's a little bit more amorphous, largely because the reality of movement strategies is really complex. There's just dozens of potentially interesting things that could be looked at. So as we play through something as simple as arm swing, so if you notice the right arm as I play through time, there's some swing. A question could come to mind. Is there a muscle effort being used? Where's the momentum of this arm coming from? Is it the body's moving and then the arm just swings as a trailing effector? Or is there actual anterior deltoid torque that's being generated at caloric cost that's giving, say, kind of like a pump, an arm pumping action? Something like that might turn on more and more and more as the fatigue in the lower body accumulates. You might think that the participant might start swinging their arms intentionally to, let's say, air quotes, gain momentum as they try to step up. Another thought too is with respect to these push-off forces, it'd be really cool if we had a second force plate placed on top of the box, so we could get a data to represent this idea, this motor strategy concept of hip knee torques being used to pull the weight of the body up onto the box. So as we'll go from here. So in the red, we'll see here there's a foot placement. Is she generating upward efforts largely by hip and knee extension, or is there a large moment here at this plantar flexor torque generation? And we could, from the biomechanics, from the force plate data, extract these peak force values, but it would be much more informative to also have a force plate at the top of the step to corroborate any kind of claim in there. So again, in this video, in this section, we're trying to figure out how do we leverage some of these kinetic and kinematic details to create a reasoned argument for a motor control component. So how is the participant maybe switching strategies from minute one to minute through minute three as this test is being undertaken? What we might remember from the caloric cost of the third minute is larger than that of minutes 1 and 2. The mechanical efficiency declines throughout the test. And we left in the last video two thoughts, one being maybe the metabolic cart data isn't valid until full steady state. That's entirely feasible. So check the literature and consider theory there. But we're working in this video through the alternate hypothesis that it is, as the machine measured it, there is a loss of efficiency over time during this test. And so we're going to look through some of this data to figure out what kind of movement strategies change. So we've got the data here. I think I can pull, I'm going to just pull a bunch of them out all together. Hopefully it won't be too messy. You'll notice that not everything tracked all the way across time, but we're going to zoom in and we'll look where we can, mostly here in this first minute. And notice, again, it's kind of messy a little bit, but we can see the red, that's the hip marker, the green, that's the knee marker, and then the blue, that's the ankle marker. And these are all in relative angles. So we're going to talk through these joint angles, and then we'll talk the trunk and foot angles are relative to fixed planes. But these are joint angles. They are segmental relative. So the hip is the neck marker to the hip marker to the knee marker. Then the knee angle that we see here is the hip to the knee to the ankle. And then the ankle angle is going to be knee, ankle, toe. So we're actually looking at relative angles. And so you might think like, these are pretty messy and they're a little bit choppy. These are time points where the system wasn't able to process all these positions. Maybe the low trunk marker was hard to distinguish. So bear with us here with the choppiness or the dashed nature of these figures. We just want to kind of get from this a relative appreciation for what's going on. So again, let's go at this frame, this hip angle. Notice that really high value, there's basically a total uprightness of the hip in the red and of the knee in the green. The ankle is about 90 degrees, so it's really not plantar or dorsiflex. And as we transition, you'll notice at this phase, there's a bit of knee flexion has begun to happen. That plantar flexion has begun to happen. There's actually, so that was actually an extension moment. Here, the knee is bent. So this is the right knee is bent. So we're at about 100-degree angle in that right knee. The hip has some flexion in it. And notice here, the foot actually, in this case, from shank to foot, is back to neutral position. So even though it's in swing, there's neither plantar nor dorsiflexor direction amount of flexion to it. So we swing through, And now we're back here in the stance. There is some flexion in the hip and the knee at the top of the step. Wondering if that's part of the participant strategy to already be prepared to be stepping back down. There's large hip, knee, and dorsiflexion moment in the ankle, and then returns back to neutral position, and then just cycles through there. So that's this data. And then we can step back and wonder what kinds of changes in these data might happen that could be interesting, right? So one thought, and this would be a decent challenge to parse out, is that as this foot comes up, as they're moving the hip and knee to get the foot up above and then placed on top of the box, there's a clearance problem, right? So we notice here that it's a requirement that the foot clears the box. I've watched through the whole video, and I think there's one or two places. I think it was a different trial that we collected that didn't get processed, where the toe actually collided with the box. So there's a clearance problem here. And so the participant is aware of that. They have to actually get their toe above the box before they can move it forward. And so we get this knee joint angle that's part of that. It's possible that over time, the minimum knee joint angle, right? So we would expect that the knee joint here, that angle being measured, would have to achieve a small, the similar small value to get this foot cleared. So if that joint angle over time, that right knee joint angle, or even the left knee joint angle changed, right, did not achieve the same minimum value as flexion occurs, then that could be indicative of a fatigue, and that would inform an increased risk of lack of clearance, right, or tripping on the box itself. So that could be an interesting thing to look through. We could step back and take even a simpler consideration. And with, again, a computational approach, we can scavenge the signal for all of the values before the step begins and find the value, what's the height of that trunk marker. So this trunk marker is going to represent, the low back marker is going to represent the center of mass. And we could potentially measure, what's the height. So that's the actual vertical displacement. We made the assumption last video that the body moves the same vertical displacement because of a fixed box height, but it's entirely possible that the elevation change is not consistent step to step. And that's actually something we'll see when we look at this trunk angle. So we could pull out what's the height, the elevation change step to step, and look at that across the entire 3 minutes and figure out, is there actually a change of elevation? Maybe that's where the inefficiency comes from, is that we assumed a fixed step height, and maybe by the end, they're achieving actually a greater step height. They're doing more mechanical work than we had accounted for last time. We'll see in this trunk angle value that that's probably the opposite of that is actually true. All right, so let's pull those data out and see. So we've got just a summary, those hip, knee, and ankle angle data, those would be some interesting things that we can pull out. You'll probably be able to find those data sets in the literature. What ends up happening is you'd have to do a lot of post-processing to this to parse out define what's the beginning and the ending of a step, pull each individual one of those out. So over 3 minutes, 22 steps a minute, there would be 66 individual steps. And so then in the same cases, right here, we'd be able to pull, this is one step event. You'd then take step 2, and you could label that step 1, step 2, and then eventually create an aggregate step that looks about like that. That is the average data from all 66 steps in the sequence, right? So in the literature, you might see a single figure that has only one curve that's marked from 0% to 100% of the phase. And what they've done is just pulled out each individual effort, averaged them over top of each other, and created a single curve. And we could do that for this, and we could then take, the first and the last and say, does it actually fit the mean? And if the last one is off the mean, then that's an indication of some kind of fatigue mechanism in there. But that's we'll just say, quite a bit of processing, and there's several decisions that have to be made to do that effectively. So for now, we'll just let you know that's possible to do with this data, but we've got a couple of things I think that might be even quite a bit simpler to comprehend, to pull out and appreciate. The next one, I think it's going to be the one that might resonate most simply for results and discussion. And we're going to calculate this trunk angle. So I'll quickly let you know how that's calculated, and then we'll evaluate what the data itself looks like. So we took a vertical line, right? And then we took the cervical and lumbar markers and drew a line there. And then we calculated the angle between those. So what's this angle? So we'll call that angle theta, and that's the value that's on now this the y-axis here of the plot. So we see across time, at only one point did that value go below 0, and maybe we can zoom to that and see why. But almost always that value is more than 5. So as you see, even in this frame, there is what the numbers will indicate to be a forward lean. One might ask, why would we use the cervical and lumbar markers? Doesn't it make more sense to do something like a cervical and a greater trochanter marker, something through the hip? And I would totally agree with that. But the problem in our case is that the participant's arm is almost always crossing the visual plane with that hip marker. And so we just have a lower confidence on that. So we have, for better or worse, methodologically decided to use cervical through lumbar against a vertical axis to tell us if there's a forward lean. There's an importance to that. If we were looking at before, we talked about these hip, knee, and ankle angles, looking at segment to segment angles. A problem with that for the trunk angle, if we were looking at the forward lean of the trunk, the thigh segment is moving all of the time. And so it's really impossible to differentiate whether that hip flexion angle is changing because of the knee elevating, if there's a a thigh rotating around the hip segment, or if it's the trunk rotating around that hip joint center. So setting that vertical line and calculating that angle relative to the pure vertical is going to give us a direct data to respond to the question, is the participant leaning forward more later on in the trial? So without processing, to report this in a journal, we would actually need to go through and parse out all of these values. For now, I think it's fair and reasonable to just do a visual inspection and report on that. And so I've got this blue line drawn across here and representing on the first couple of efforts, you see there's only about 20 degrees of trunk lean angle and very little in the first minute exceeding that value. And as you go into the second and third minute, so in that third minute here, we're actually seeing a lot of signal is in excess. So you probably could fairly quickly in the software, it's a little more computationally intense than what we expect in the case study here. You can calculate the mean here and find out that the mean value of, let me actually draw more there, somewhere there. So the mean value of trunk angle is probably around 15 in the first minute, and it's probably somewhere exceeding 20 in the third minute. So we could just take this as visual inspection. We could probably grab these data and do that in Excel with an average statistic for that first 60 seconds and the last 60 seconds of this data signal, and just put a report. Maybe we'll prepare that and share that with you. That you can be able to claim that there is a change of average trunk angle in the third minute. So much more tricky would be to find all of these peaks. So it's the maximum trunk angle at a time and do statistics on that. Let's just watch through the video really quick and notice, maybe I can zoom in just so we can appreciate what's happening with the trunk angle as time goes along. So you see there's a forward lean, and then as the feet come up, there's more of an uprightness, much more upright there. And then it seems like at the initiation of every step, there's a forward lean. And so we could go through and pull that out and take a little bit more math than we're prepared to do in terms of time series analysis. But just so we can zoom in, you can see what that looks like. These two peaks are the going up, and then the second peak there, and that complex is the coming down. So each two peaks is a whole step, and that's a feature. So again, I think it's a fair and reasonable observation to just pull this plot through and say that the trunk angle increases throughout time. And you can just take the screen cap of this and mark it up, or we can get the data set exported and we can do some math statistics in Excel. So either way, I think this really may explain a lot of the loss of efficiency, because if you think about it, when you're in this forward trunk lean position, you now have the more lean there is, the more force necessary in these spinal erectors to maintain that position. The trunk is a fairly massive segment. And so any, every 5-degree forward lean is going to cost that much more muscle effort to control the trunk during that movement. So I think it's a reasonable argument to present this data in a results section and then put the conversation and the discussion that the forward lean and maybe a primary component of reduced efficiency. It might be interesting to contemplate why the forward lean would be the strategy selected by the participant. Is there actually, with a forward lean, a reduced elevation? So can we go here and see with the trunk leaning farther forward, even when it's on the step, is the center of mass just a little bit less high, maybe by a couple of centimeters. And so there's some energetic savings by getting trunk lean there, even though it's costing more muscle force. It could be offloading force necessary in the glutes and quads, maybe some of this propulsive plantar flexor torque, muscle force, and not everybody moves intelligently. So there can be some misperception of cost savings by having this forward lean that feels like not stepping up so high. That's hugely speculative and warrants a dive into literature to see, is there any basis for that? Or is there something else that explains this effect much more reasonably? So I think with that, I did want to take a look at this with y'all and see what happened here. And it's really difficult to tell. I'm wondering if the processing of the marker had jumped, so we wouldn't be able to see that in this video. It's entirely possible that this is taking cervical, lumbar markers against the vertical. It could actually be that in here, the lumbar marker got mismarked onto one of these others instead. So I'm guessing that's what happened. Maybe it was the cervical marker got replaced by the, sorry, I guess it would be the low back marker maybe got replaced by the trochanter or the elbow. So this probably is explained well by poor processing or not correcting a processing error. So if you see something like that in a data set, you shouldn't just take it from face value. It's unlikely that one of these steps is going to be so atypical from the set. So you can skim over that and take that global perspective evaluation, and just know that if you're going to do data processing, motion capture, marker processing, and cleaning, takes a decent amount of time, attention, and it's quite a bit more complicated than just getting force values from a force plate. Metabolic cart put a lot of work to get it calibrated, and you pretty much get your data straight out. Motion capture, you gotta get a lot of work getting your markers placed. Most of the work is in the software to get these markers processed so that you can believe that these positions actually reflect the reality that was observed. So there you go. Maybe a couple of interesting details that you can place in the results, something to discuss in the discussion section. Keep in mind that you might want to have a figure or an appendix that indicates on a skeleton map all the placements of these markers during the test. Some of the methods, if you want to discuss the trunk angle data and present a chart like this in the results, it's got to be described in the methods. Your readers shouldn't be surprised to see data that's not anticipated. So you need to have some sort of method explaining that trunk angle was calculated, how it was calculated relative to the vertical, and then you can drop a plot like this and it could make sense. So again, like I said in the last video, results are results, just an objective statement of what was measured. The discussion is the place where you can describe the meaningfulness of it, associate that finding with some of the other findings, with the broader literature, call to question, maybe there's a limitation to it, and discussion in the discussion. I think this kind of wraps up the whole case study effort. The intention being, what's the clean step test? What happens if we add lab instruments to it? Can we understand more about how the physiology, mechanics, and motor control integrate to create this movement behavior? Conclusions depends on your purpose statement, as you wrote in your introduction section. It could be every step test from now on should be instrumented. It could be something like force plates add confidence in metronome adherence. It could be something along the lines that the efficiency factor. So if something happens over the 3 minutes, that people get less effective or less efficient in their step behavior. And here's some data that helps explain that. But just make sure as you work on these case study reports that your introduction, the purpose statement, and your eventual conclusions should have good alignment. The introduction should prepare the reader for the methods that you deployed. The methods lead to the results. If you didn't report the method, they're going to be surprised by the results. So just make sure that the whole time that there's alignment between sections. The discussion is there so that you can unpack the findings against the literature, reflecting again from the introduction to make sure that it's one whole narrative story throughout the document. So don't hesitate to put figures, tables, appendices as needed to make sure that it's maximally clear to the reader and tells a good, clear, coherent story that can inform future work. Okay, thank you.